Welcome, class. So, last time we looked at this idea of stoichiometry, and now that we have a better understanding of how to go from how much of one material in a balanced chemical reaction we have to then calculate how much of another material, a product or a different reactant, that we need or can make. So now that we have that basic idea, we can start to add a little bit of wrinkle to it. Right? And so, in all the problems that we saw last time, we were given one material to start with and asked how much of another material we could make or we needed, etc. But what if we're given more than one material, right? What if we're told that we react this much of this material with this much of another material, and we want to know how much of this material we'll make? How do we know how to start our calculation, right? And so this is what we're going to talk about today. So this is what we refer to as a limiting reactant or limiting reagent problem. So in other words, we have to determine which of these two reactants is going to limit the reaction, or in other words, is going to be used up first, right? And of course, once one of our reactants runs out, then the reaction will stop. So we have to know which reactant is going to limit how much product we can make. Now, as we go through this process, we're going to encounter some terms, right? The first one is called a theoretical yield. And we've already calculated one of these, we just didn't call it that. And so the theoretical yield is the amount of product that can be made in a chemical reaction based on the amount of limiting reactant. So we did this last time when we calculated how much carbon dioxide can be made from a given amount of octane, right? That's a theoretical yield. The difference is, in those problems, we were essentially told what the limiting reactant was, right? Because we were only given one material, and so then we just could calculate the amount of product we could make. That's a theoretical yield, right? The amount of product, the maximum amount of product that could be produced in a chemical reaction based on the amount of limiting reactant present. Now, the actual yield, or sometimes called an experimental yield, is the amount of product you actually produce in a chemical reaction, right? In an actual experiment. So this is a lab result, right? This is an actual number that you make in a lab. Now, the actual yield should always probably be less than the theoretical yield, right? It should never be more than the theoretical yield because that's the maximum, but is almost always less. Now, percent yield is simply the ratio of those two, right? It is the actual yield divided by the theoretical yield times 100 to put it in terms of a percent. So we're going to work with these different terms as we go through these problems. So how do we approach this? How do we determine what the limiting reactant is? And there's no real secret way here, right? Essentially, what we're going to do is we're going to conduct the process that we did last time. So starting with the mass of what we know and calculating the mass of whatever product we're interested in. But we're going to do it at least twice, right? We're going to do it starting with each amount of reactant that we're given. So, for example, if we were given an amount of sodium that reacted with some amount of chlorine to produce sodium chloride, and we wanted to calculate the theoretical yield of sodium chloride, we would have to determine which of these was the limiting reactant, sodium or chloride. So what we would essentially do is calculate the theoretical yield based on each of these materials, right? So we would start with the grams of sodium, and we'd go through our process, convert it to moles of sodium, use the ratio between sodium and sodium chloride in our balanced equation to get moles of sodium chloride, and then get grams of sodium chloride. And then we would do the same thing, but instead of starting with the amount of sodium, we would start with the amount of chloride that was given to us. And we would, use its molar mass to convert to moles of chlorine. Use its ratio, the ratio between Cl2 and sodium chloride. Right? So notice the ratio we're using is the ratio involving just the materials that we're looking at in this equation or this calculation. So we get moles of sodium chloride and we would convert that into grams. And the key is we're going to then look at these two numbers and compare them. And the smallest amount must have come from our limiting reactant, because what that's telling you is that after I made that amount of sodium chloride, the material was gone. And so whichever of these is smallest, that tells me it came from the limiting reactant, and therefore that result would be the theoretical yield. Right? That would be the most we could make when we combine those two amounts of material. Okay, so enough talking about how we would approach it. Let's do some actual calculation here. So we're going to stick with that same reaction, but in this one, we're going to have the numbers. So if 53.2 grams of sodium were reacted with 65.8 grams of Cl2, we want to find the limiting reactant and the theoretical yield. Now, it should say, of course, of sodium chloride. Now, it's kind of assumed here because there's only one product. If there's multiple products, of course, they have to tell you which product they're interested in. Okay, so here's where we're going to go. So it doesn't matter which one you start with, but the key is not to get yourself confused, right? We only want to focus on the connection of two materials at a time. So first, say we're going to start with sodium and look at, if I start with 53.2 grams of sodium, how much sodium chloride can I make? Then we're going to do a second one. In that one, we're going to start with the chlorine. And we're only going to worry about, if I start with that much chlorine, how much sodium chloride can I make? And so we don't want to mix up the two things, right? So first one, we're going to start with our sodium. So we have 53.2 grams of sodium. Now we're going to go through our process. It's the same process we did last time. So we have to convert our grams of sodium into moles. So we have grams of sodium down here, moles of sodium here. If I look on the periodic table, right, 22.99 grams per 1 mole of sodium. So now I've canceled out my grams. So now I have moles of sodium. And I want to get, remember, moles of sodium to moles of sodium chloride. So I look for that ratio. Right? So for every 2 moles of sodium I use, I can make 2 moles of sodium chloride. And so the sodium was on the bottom, so it cancels. So now I'm left with moles of sodium chloride. Now, last step is to take the moles of sodium chloride, put them in terms of grams. And to do that, I need the molar mass of sodium chloride. So molar mass of NaCl equals 22.99 grams per mole for the sodium plus 35.45 grams per mole for the chloride. It gives me 58.44 grams per mole for sodium chloride. So 58.44 grams of sodium chloride per 1 mole of sodium chloride. Of course, that cancels out, and our answer will be in grams of sodium chloride. So if I go through and do the math, noting that I started with a number that has 3 significant figures, so my answer can only have 3 significant figures, we should end up with 135 grams of sodium chloride. So that's how much sodium chloride I could produce if I started with 53.2 grams of sodium. So now I got to do the same thing, but I got to start with my Cl2. So I'm going to start with 65.8 grams of Cl2. Of course, I'm going to use my molar mass, so 1 mole of Cl2 gives me a certain number of grams. So if I look on the periodic table, chlorine 35.45, so 2 times 35.45 equals 70.90 grams per mole. So that's going to cancel out my grams of chlorine. So now I need to convert from the grams, from the moles of chloride to moles of sodium chloride, right? So I got to use that ratio. So in that ratio, right, I can make 2 moles of sodium chloride for every 1 mole of Cl2. So that cancels out my moles of Cl2, gives me moles of sodium chloride, and the last step, of course, is to convert moles of sodium chloride into grams. So again, 58.44 grams of NaCl per mole of NaCl. And if I go ahead and do my math, moles cancel. I'm left, again, 3 significant figures, 108 grams of sodium chloride. So now I simply look at these and say, okay, which one is smaller? Well, the 108 is smaller. So that means if I start with 65.8 grams of chloride gas, it's going to run out after I make 108 grams of sodium chloride. So that's going to cause the reaction to stop. Right? So even though I can make more sodium chloride from the sodium, I don't have enough Cl2 to do that. The Cl2 is going to limit my reaction, so I can only have a theoretical yield of 108 grams of sodium chloride. And since that came from the Cl2 equals my limiting reactant. Okay, so now I've identified my limiting reactant as Cl2. I've identified my theoretical yield of sodium chloride as 108 grams. Now, that's where a lot of problems will end. But we're going to add one extra step onto here, and sometimes as a follow-up, these will get into percent yields. So they'll do something like this. They'll say, okay, well, now, if you do an experiment and your actual yield is 86.4 grams of sodium chloride, find the percent yield. Okay, well, I know that my percent yield equals my actual yield divided by my theoretical yield times 100. So I got 86.4 grams of sodium chloride divided by 108 grams of sodium chloride times 100. So I do that, I get 80.0%. Now, again, think about significant figures when we do this, right? So you may do this on your calculator and you get, 80 or, but we have to remember, since both of these numbers have 3 significant figures in them, we should keep 3 significant digits in our percentage. So that's why my percent yield here would be 80.0%. Okay, so now we've run through a classic limiting reactant problem. And again, it's a little bit more time consuming, but there's no tricks involved, right? It's the same reaction, the same calculations that we learned the last time, but now we just have to do them with each reactant and then compare to find our limiting reactant, and then we can potentially calculate a percent yield. Now, this concludes the material for this chapter. I am going to, after this, do one other example if you think that would help you. So, this is just going to be, the next part of this is just going to be doing one more final example. And if you find that useful and you want to look at that, well, keep listening or come back, check it out later if you want another example. Okay, here I'm going to go through one more example of a limiting reactant theoretical yield type problem. If you need to see it one more time here. So, in this reaction, we have copper oxide reacts with carbon to give copper and CO. Okay? And before we do any of this, of course, we should always make sure that it's balanced. This one looks balanced, and it is, right, with a 1, 1, 2, 1, right, as our coefficients. And in this particular problem, I'm reacting 11.5 grams of carbon with 114.5 grams of copper oxide. I want to find the limiting reactant and the theoretical yield of copper, right? And once I do that, if the actual yield of this experiment is 87.4, what was my percent yield based on the theoretical yield that you're going to calculate first? Okay, so again, just like the last problem, the key is to sort of identify, what we need to look at. So we're reacting an amount of carbon and an amount of copper oxide, and the key is we're interested in the theoretical yield of copper. We could care less about the CO. Right? We're going to ignore the CO. It's not what we're interested in here. And so, again, we're going to look at two different calculations. We're going to go from carbon to figure out how much copper we can make. And then we're going to start with our copper oxide and figure out how much copper we can make. And then, based on those two results, we can determine which one of those two reactants is limiting our yield of copper. So let's lay out the calculations. So we're going to start with 11.5 grams of carbon, which the first step here is to convert into moles of carbon. So if we look on the periodic table, 1 mole of carbon, 12.01 grams of carbon. So once we've converted the carbon into moles, we need to use our relationship in our equation to convert it into moles of copper. So if we look at our coefficients, right, for every 1 mole of carbon I react, I can make 2 moles of copper, right? And lastly, we're going to take our moles of copper and convert it into grams of copper. So again, looking on the periodic table, 63.55 grams of copper per every mole of copper. Again, we set it up that way so that everything cancels out. So we're using our dimensional analysis, so our grams of carbon cancel out here, our moles of carbon cancel out here and here, and our moles of copper cancel out here and here, and we're left with our target on top of grams of copper. So if we go through, do this calculation, we should come up with an answer. We want to leave it as 3 significant figures based on the initial number that we're given. So that's 122 grams of copper should be what I come up with. Okay. So now, I turn around, we've got to do the same thing, but starting with 114.5 grams of copper oxide. Again, first thing, right? Got to convert it to moles. So 1 mole of copper oxide. Now, we got to calculate a molar mass here, so I'm going to do it up here. So we got 2 times 63.55 grams per mole for the copper, plus 1 times 16.00 grams per mole for the oxygen. We put all that together and we have 143.1 grams for every mole of copper oxide. So now that my grams of copper oxide to cancel, so now I can go back, and if I look at my equation, for every, I can make 2 moles of copper for every 1 mole of copper oxide. So that's going to cancel out my moles of copper oxide. So the last thing I need to do here is again convert it into grams of copper. So 63.55 grams of copper per every mole. So if I carry out my calculation, give my answer. Now this time my answer can be given to 4 significant figures because I have 4 significant figures in my starting. So I come up with 101.7 grams of copper here. So I'm going to again look at these 2 numbers, and I'm going to look at which one's smaller, and that's going to be my theoretical yield. So after I make 101.7 grams of copper, my copper oxide runs out, right? That's the maximum I can make. So that means my copper oxide here is my limiting reactant in this particular problem. So the copper oxide is my limiting reactant, and 101.7 grams of copper is my theoretical yield. Now the last part of this asks me to look at what if I did this reaction but only made 87.4 grams of copper. What's my percent yield? So my percent yield equals the 87.4 grams divided by my theoretical 101.7 grams times 100%, and I get a theoretical yield, or excuse me, a percent yield of 85.9% yield. Again, the 3 significant figures here is coming from the 3 significant figures in my actual yield, my 87.4 grams here. So 85.9% yield. So there's one more example. Now, as with all of these calculations, especially these new ones, right? The more practice we can do, the more examples, the homework problems in the back of the book, the more comfortable we can get in solving these different kinds of problems.